Let's talk about the Venturi effect. This has to do with water or any fluid flowing through a pipe. And it turns out, let's say this water's flowing right here, minding its own business, having a good day for that matter, when it meets a constriction. What's going to happen here? Well, the water's got to keep flowing, but it's going to start flowing faster through the constricted region. And the reason is, well, there's a certain amount of fluid that's flowing through this pipe. Let's say all the fluid in this region right here, let's say this front part of the water, I mean this whole thing's filled up, but just say this cross section of the water happened to make it from this back portion to this front portion in, I don't know, let's just say 1 second. So this entire volume moved through this section of the pipe in 1 second. Well, there's a law in physics that says that same volume's got to make it through each portion of this pipe. Because if it didn't, where's it going to go? This pipe would have to break or something. This water's got to go somewhere. If that much flowed through here in 1 second, then this much has to flow through this little tiny region in 1 second. But the only way that that's possible is for the front surface, instead of just traveling from there to there in 1 second, the front surface is going to have to change its shape, but the front part of the water is going to have to travel from here to here, maybe in a quarter of a second, because all of this has got to cram through here in the same amount of time, because that water's still coming behind it. There's more water coming. And the volume flow rate's got to stay the same. The volume per time flowing through one region of the pipe has got to be the same as the volume flow rate through some other region of the pipe, because this water's got to go somewhere. It doesn't just disappear in here. It's got to keep flowing. That means the important part is the water flows faster through the constricted region. Sometimes much faster through the constricted region. The smaller this is compared to this original radius, the faster the fluid will flow through here. Why do we care? Well, because faster moving fluid also means lower pressure. Why does faster moving fluid mean lower pressure? Well, if we look at the Bernoulli equation, Bernoulli's equation says P1 plus rho g h1 plus 1/2 rho v1 squared equals P2 plus rho g h2 plus 1/2 rho v2 squared. Oh my goodness, this looks frightening, but look at P1. We just pick some point in the pipe. Let's just pick this point right here. We'll call that point 1. So all these ones, this whole side refers to that point. Let's just pick point 2 right here. All this whole side refers to that point. Now notice something. These are like basically the same height. And assume height's not really a big difference here. So let's cross out the heights. They're the same height, so we don't have to worry about that. This says that, all right, if there's some pressure at 1 and some velocity of the water at 1, you can plug those in here and get this side. But now look at over here. We know the velocity at 2 is bigger. We just said that. It has to be because the volume flow rate's got to stay the same. So this speeds up in here. So this is bigger, this quantity here. But we know the whole thing equals this side. So if this term increased, that means the pressure's got to decrease so that when they add up, they get the same as this side over here. This is actually called Bernoulli's principle. Bernoulli's principle says that when a fluid speeds up, its pressure goes down. It's totally counterintuitive. We always expect the opposite. We think fast moving fluid, that's got to have a lot of pressure, but it's the exact opposite. Fast moving fluid actually has a smaller pressure, and it's due to Bernoulli's equation. And this is what causes the Venturi effect. The Venturi effect refers to the fact that if you have a tube and you want a smaller pressure region, you want the pressure to drop for some reason, which actually comes up in a lot of cases, just cause a narrow constriction in that tube. In this narrow constriction, faster moving fluid, and it'll cause a lower pressure. This is the idea behind the Venturi effect. So the Venturi effect basically says for a constriction in a pipe, you're going to get a lower pressure. While we're talking about fluid flow, we should talk about one more thing. Let me get rid of this here. Imagine you just had a brick wall with fluid flowing towards it. Maybe it's air here. So they've got some fluid flowing towards this brick wall. This seems like a really dumb example of Bernoulli's principle, but I'm going somewhere with this, so stay with me. This is flowing towards here. What's going to happen? Well, it can't go through the wall. It's got to go somewhere. Maybe this just goes up like that, and this, I'm going to go this way. It's closer to go that way. This side maybe just goes down. This is actually kind of what happens. But there'll be a portion in the middle that basically just terminates. It hits here and kind of just gets stuck. So there'll be some air right near here in the middle where it's just not moving. What if we wanted to know what the pressure was there based on the variables involved in this problem? We can use Bernoulli's equation again. Pick 2 points. Let's pick this one, 0.1. Let's pick this one, 0.2. Use Bernoulli's equation. It says this, and again, let's say these are basically the same height, so that height is not a big factor, and if these terms are the same, then we can just cross them out because we can subtract them from both sides. They're identical. Now what can we say? We know the velocity of the air at 2. It's not moving. It got stuck here. It got stagnant, and so V2 is just 0. And we get this statement that the pressure at 2, which is sometimes called the stagnation pressure. So I'm going to call it the stagnation pressure because the air right here gets stuck and it's not moving. You might object. You might say, wait, hold on. I thought the air had to go somewhere. Well, it's all going somewhere. The point is there's some air right here that gets stuck. It gets stuck and air starts passing it by. And so what's this pressure here? Well, up here we just read it off. All these went away. P2, which is what I'm calling the stagnation pressure, got to equal P1, the pressure over here, plus 1/2 rho V1 squared. And we get this formula. You might think, why would we care about this? Who is regularly shooting air at a brick wall? People do it all the time because you can build a pretty important instrument with this called a Pitot tube. And the Pitot tube looks something like this. Let's get rid of that. So why would someone use this system? It's called a Pitot tube. People use it to measure fluid velocity, or if you're moving through the fluid, it's a way to measure your velocity or your speed. So what happens is you've got this setup. Let's say you're in an airplane. You mount this on the airplane. You're flying through the fluid, which is the air. So that means air is rushing towards this section here, rushing past you. Let's say you're flying to the left. So you'll notice air flying past you. A Pitot tube always has this section that's facing into the wind or into the air. This air would be directed straight toward this region. And the key is this is blocked off at the end. So there's air in here, but it can't be moving. The air in this section can't be moving all the way to the front because, where's it going to go? We just said if fluid flows in, fluid's got to flow out. There's no out here. And then there's another region. Up here, you've got a second chamber where the air flows over the top, and this is directed at a right angle to that airflow. You've got another chamber, and again in here, fluid's not flowing. The key is, this gives you a way to determine the difference between the pressure here and the pressure there. If you had some sort of membrane in here, something dividing these two sections that could tell you the pressure differential, right? If the pressure on this side is a little bigger than the pressure on this side, then this would bow outward. One of these is measuring the pressure here, and one of them is measuring the pressure there. What's the relationship? It's the one we just found right here. This is the stagnation pressure, right? The air's not moving in here. It flows straight in. We know the V is 0 right here. And so the stagnation pressure equals the pressure up here. Again, I'm assuming there's very little height difference. Let's say this is a very small device and it's not like 10 meters tall. So any height differences are minuscule. And we would just have our same equation before. This would just equal the pressure plus 1/2 rho V squared. And this is how you determine the velocity or the speed, because now we can just solve this for V. I'd get that V1 equals PS, the stagnation pressure, minus the pressure at 1. That whole thing times 2 divided by the density of the air, and then a square root because you have to solve for the V1. So this device lets you determine this pressure differential right here. Check. You need to know what the density of air is, and this gives you a way to determine the velocity of the fluid, or in other words, the velocity of your aircraft flying through the air.